In this lab, I'll introduce some practical aspects of resistors, resistance, and Ohm's law. This will include experimentally generating a resistor's voltage current characteristics. The techniques we'll introduce here can be applied to automatically generate the IV characteristics for an arbitrary circuit element. This process is commonly called curve tracing. Resistors are usually used in electrical circuits to limit current or to set voltages to desired levels. Resistance is a property of materials which, as the name implies, measures how much the material resists the flow of current. Since voltage is used to cause current to flow, resistance indicates the amount of voltage required to move a given amount of current through a material. So less current flows through a high resistance than through a low resistance if the same voltage is applied to both. Resistance has units of ohms, which are represented by the Greek letter omega. Typical resistance values can range from ohms to thousands of ohms or millions of ohms. Thousands of ohms are called kiloohms and are represented by a K prefix, while millions of ohms are called megaohms and are represented by an M prefix. This is the symbol for a resistor. Resistors can have some voltage difference, V, across their terminals, and a current I entering the positive voltage terminal. Circuit elements are described by the relationship between voltage and current at their terminals. For resistors, this relationship is Ohm's law. Voltage is equal to current times resistance. In the lab assignments, we'll be mostly interested in the practical aspect of things. So in this video, we'll emphasize the measurement of resistance and some good data acquisition and analysis practices. There are several ways to determine the resistance of a given resistor. Resistors often have their nominal resistance encoded directly on them in some way. For example, many resistors have a series of colored bands painted on them which provide a code from which you can determine the resistor's resistance. The values printed on the resistor are, however, not entirely accurate. The actual resistance will almost always differ somewhat from the expected value. Therefore, when we're presented with a resistor, it's beneficial to verify its resistance with some measurement. Probably the easiest way to measure resistance is with a digital multimeter. DMMs invariably include a resistance measurement function called an ohm meter, which displays the resistance of a resistor to which it's connected. It's also possible to apply power to a resistor, measure the resistor's voltage difference and the current through the resistor, and use the relationship between voltage and current to calculate the resistance via Ohm's law. In this video, we'll talk at least briefly about all of the above approaches. We'll spend most of our time, however, on the last option, since it's the most fundamental of the three. It illustrates the measurement of the voltage-current relations for a circuit element. That concept is very broadly applicable to lots of types of circuit elements. Special purpose instruments that measure and plot an element's current as a function of voltage are called curve tracers. First, I'll introduce some typical physical resistors. Resistors come in a wide variety of styles. In this video, I'll emphasize resistors that are used to create circuits using solderless breadboards. This is a large wire-wound power resistor. Resistors like this one, which are physically large enough, will often have the resistance value printed directly on the side. This is a 6.2 ohm resistor. Notice that on this resistor, the maximum power dissipation is also listed, 10 watts. This is another fixed resistor. It has a resistance of 1 megaohms. Notice that the physical size of the resistor doesn't correlate to the resistance value. The physical size is more closely related to the maximum power that the resistor can dissipate. The 1 megaohm resistor has a maximum power dissipation of less than half a watt. So far, the resistors I've shown have been fixed resistors. That is, their value is a set value which can't be adjusted. Resistors with variable resistance are also available. This device, for example, is called a potentiometer, or a pot for short. These components have a resistance which can be changed by adjusting a screw on the side of the resistor. Most of the resistors we'll use in this course are these small carbon resistors. The resistance of these resistors can be determined from the colored bands on their side. Next, I'll talk about determining a resistance from the resistor's color bands. Resistors can have either 3, 4, or 5 color bands. This is a typical 4-band resistor. This means that the resistance value and its tolerance are coded in 4 colored bands on the resistor. The first 3 bands consist of a resistance value in exponential notation. The 4th band is the tolerance, which tells us the allowable error between the actual and nominal resistance of the resistor. The colors of the first 3 bands indicate the digits 0 through 9. Black is 0, brown is 1, red is 2, and so on. A complete table of colors is provided in the next slide. The first 3 bands are read as follows to get the nominal resistance. The general formula is shown here. The first 2 bands, A and B, represent a 2-digit number which provides the mantissa of the resistance. The 3rd band provides an exponent or power of 10 by which the mantissa is multiplied. For example, if the first 3 bands are brown, black, red, the value is 1 for brown times 10 plus 0 for black times 10 to the 2nd power, since red corresponds to 2. This is 10 times 10 squared, or 1,000 ohms. The 4th band is the tolerance. It's a number that provides the maximum error between the expected and nominal resistance of the resistor as a percent of the nominal resistance. A gold band, for example, means that the actual resistance value will be within 5% of the value coded on the resistor itself. As I mentioned previously, resistors can have various numbers of bands. This table provides coding for all possible variations. I won't spend time on this, since if you can read a 4-band resistor, you can use the table to read any of the other codes. For a 4-band resistor, the first and second columns of this table indicate the mantissa, and the 4th column gives the exponent. Now let's take a look at an example of using the color codes to determine a resistor's nominal resistance, and then using a digital multimeter to measure the resistance. This resistor's color codes are brown, black, red, and gold. Brown is 1 and black is 0, so that's 10. Red is 2, so that becomes 10 times 10 squared, which is 1,000 ohms, or 1 kiloohm. Let's check the resistance with a DMM. In order to measure resistance, set the selector knob to the ohm symbol and insert the DMM leads into the COM and volt ohm ports. If the resistance between the leads is too high for our DMM to measure, as in the case where there's nothing between the leads, the DMM display reads OL. This stands for overload and simply means that the resistance is higher than the DMM can register. When I clip the DMM leads to my resistor, I get a measured resistance of 0.99 kiloohms, which is 990 ohms. Since the tolerance band of this resistor is gold, the measured resistance is well within 5% of the nominal value. Now let's use a DMM to set the resistance for a potentiometer. The maximum resistance for this device is encoded on the side of the pot as 3 numbers. The first 2 numbers create a 2-digit number. This 2-digit number is multiplied by 10 raised to some power indicated by the 3rd number. Our potentiometer is encoded as 103, so its maximum resistance is 10 times 10 to the 3rd, or 10 kiloohms. The actual resistance of the potentiometer can be adjusted to any value between about 0 and that maximum resistance by turning the set screw on the end of the pot. The potentiometer has 3 terminals with which to connect it to your circuits. The resistance between the 2 outer pins is simply the maximum resistance of the pot. The resistance between these pins does not change as you turn the set screw. The resistance between the center pin and either of the 2 other pins does change as you turn the set screw. Since this is a variable resistor, we can't tell what the actual resistance is without measuring it. Typically, we measure resistance with a digital multimeter, or DMM. Let's do that now and see how the resistance changes. To measure resistance, we set the DMM knob to the ohm symbol, Plug the leads into the volt, ohm, and comm terminals, and then connect the leads to the resistor pins. I'll use the center pin and this outer pin. Currently, this resistance is about 5.2 kilo ohms. If I change this screw position, the value of the resistance changes. Now let's talk about estimating resistance from a measured voltage and current. Ohm's law tells us that voltage is equal to resistance times current. If we rearrange this, resistance is the ratio of voltage across the resistor to the current through the resistor, or R is equal to V over I. This is a circuit we can use to measure resistance. It consists of a voltage source used to apply power to the circuit and an ammeter to measure the resistor current I. If we measure the voltage V across the resistor, we can use that measured voltage and the measured current to estimate the resistance by taking the ratio of the voltage to the current. I'll demonstrate this process next. This is the circuit I created to estimate resistance. I'm using the Analog Discovery 2 Supplies instrument as my voltage source V sub S. I'm also using the Discovery to measure the voltage across the resistor using the voltmeter instrument. I'm using a digital multimeter to measure the current through the resistor. The A port on the DMM is connected to this red lead, and the COM port is connected to this black lead. The circuit itself is extremely simple. It has one resistor. Its color bands are brown, black, brown, which corresponds to a resistance of 100 ohms. The voltage source is this red wire. It's V plus on the Discovery. The source is relative to ground, so the negative terminal of the voltage supply is this black wire. Channel 1 of the Discovery's voltmeter, the orange wire and the orange wire with a white stripe, is connected to the resistor terminals to measure the voltage across the resistor. The orange wire is at the assumed higher polarity, so that has to be connected to the positive terminal of our assumed voltage on the schematic. The A port of the ammeter connects the V plus terminal to the resistor. Remember that on our schematic, positive current was assumed to enter the positive terminal of the resistor. The DMM assumes that positive current enters the A port. Those assumptions have to be consistent for the data to make sense relative to the mathematics. To measure current, I'll move the knob on the DMM to the A setting. Now let's set up the Analog Discovery to apply power to the circuit and measure the resistor's voltage. The Discovery's variable power supplies are controlled by clicking on the Supplies button under the Welcome tab. I'm using the positive supply, so I can disable V minus. The voltage level I'm going to use for V plus is 2 volts, and I click on the Master Enable button to turn on power. The voltmeter instrument is under the voltmeter icon on the Welcome tab. If I click on Run, I'll start measuring voltage. I want the DC levels. I've got 1.98 volts across the resistor. The ammeter is indicating that there's 0.02 amps. Resistance is voltage over current, which is 1.98 over 0.02, or about 99 ohms. This is extremely close to the nominal resistance of the resistor based on the color bands. One final comment on estimating resistances from measured voltages and currents. In our previous demo, we acquired only one piece of data from which to estimate resistance, a single combination of voltage and current. Since errors can always creep in when we're acquiring data, any single data point is subject to an unknown amount of error. A better approach is to acquire data with a variety of different voltages and currents. With multiple points, we can get a better estimate of the overall resistance and identify outlier or bad data points. With multiple points, we can plot the various combinations of voltage and current against one another. Then we can draw a line that we think best represents the data. The slope of the line will give the resistance. Individually measuring a large number of voltage and current combinations is pretty tedious. Luckily, there's a way to more or less automate plotting these characteristics. To do this, though, we need to apply and measure a time-varying voltage to our circuit. We can use a waveform generator to apply varying voltages and measure time-varying voltages using an oscilloscope. Say that we apply a triangular voltage waveform like this one to a resistor. The resulting current will also be a triangular waveform. Each point on the current curve will simply be the corresponding point on the voltage curve divided by the resistance. If we measure a bunch of combinations of voltage and current points and plot the voltage points against the current points, we'll have a plot of the voltage as a function of current. Now let's look at this idea in a little bit more detail. We've applied a voltage as a function of time to the circuit and measured the corresponding current. These points are the measured values that I'll use to illustrate creation of voltage-current curves. The current I1 corresponds to the voltage V1, so if I plot these two data points against one another, I get 1 point on the IV curve. I can do the same thing with I2 and V2, which gives me this point. If I do this with a lot of these data points, I get a bunch of data points that should lie on the line relating voltage and current. Since any measurement has errors, these points will probably not lie exactly on the line, but I can draw a line that I think best fits the data. This approach should minimize the error associated with any single data point. The slope of this line is 1 over the resistance, since I put current on the vertical axis and voltage on the horizontal axis. If I put voltage on the vertical axis and current on the horizontal axis, the slope of the line is the resistance. It doesn't really matter which plot you create. They both contain the same information. Now let's talk about some of the practical aspects of performing this process. 2 instruments are generally required, both of which work with voltage as a function of time. Function generators can apply time-varying voltages, and oscilloscopes can measure time-varying voltages. The problem is that we don't typically have a device available that measures a time-varying current. But we can use Ohm's law to infer the current from the voltage across a known resistance. As an example of this process, consider this circuit. We put a 100 ohm resistor in series with the resistor we want to characterize. The current through the two is the same, which we can prove by applying Kirchhoff's current law here. If the voltage across the known resistor is V1, we can calculate the current as V1 over 100 ohms. We can then plot the voltage V2 against this calculated current to get our voltage current characteristic. This curve tracing process can be done pretty much with any 2-channel oscilloscope, meaning that the scope can measure 2 different voltages, and a waveform generator. I'll use Digilent's Analog Discovery 2 USB-based instrument to demonstrate the process, since I can do screen captures to show the interfaces, and most of the necessary calculations can be automated directly within the instruments without downloading and post-processing the data. The lab assignments with this course do contain instructions for performing this process with other instruments. My circuit consists of a known 100 ohm resistor and a resistor I want to characterize. I'll apply a voltage to this combination with channel 1 of the waveform generator, this yellow wire. The voltage is relative to ground, so a black wire is used as the negative terminal of my voltage source. I'll use channel 1 of the oscilloscope, the orange wire and the orange wire with a white stripe, to measure the voltage across my known resistor. I'll use channel 2, the blue wire and the blue wire with a white stripe, to measure the voltage across the unknown resistor. Now let's apply power and create a voltage current curve for the unknown resistor. To apply a time-varying voltage, I use a function generator. On the Analog Discovery 2, I access that instrument by clicking on the WaveGen icon under the Welcome tab. This button allows us to choose a generic wave shape. A triangle wave is probably the best for our purposes at the moment. We also need to select a frequency, which is fairly arbitrary. I'll choose a frequency of 10 Hertz. The amplitude affects the maximum range of the triangle wave, which will be the range of voltage applied to the circuit. I'll use 4 volts. So that the applied voltage goes from negative 4 volts to positive 4 volts. The offset is the average value of the voltage. I'll leave that at 0. The waveform I'm going to apply is shown in this window. It's a triangle. It goes from negative 4 volts to positive 4 volts, and it has a period of 100 milliseconds. That's what I wanted, so I'll click on Run to start applying power to the circuit. Now I need to measure the 2 resistor voltages and infer the current from the known resistor via Ohm's law. I'll use an oscilloscope for this process. In the Analog Discovery 2, the oscilloscope is accessed by clicking on the scope icon under the Welcome tab. The scope interface is similar to most oscilloscopes. There's a main window where the signal will be displayed. Time is on the x-axis and voltage is on the vertical axis. The screen is divided into a grid of 10 divisions in both directions. These control buttons on the right-hand side of the window set the scales on the vertical and horizontal axes. The units are on a per division basis. I'm using a 10 Hz triangle wave, which will have a period of 0.1 seconds between peaks. If I choose a time base of 20 milliseconds per division, that will display 2 periods of the waveform since my horizontal range is 200 milliseconds. The vertical scales for channels 1 and 2 are set separately. I'll set the channel 1 scale to 200 millivolts per division and the channel 2 scale to 1 volt per division. To start measuring voltage, click on the Run button. The orange line corresponds to channel 1, the blue line corresponds to channel 2. I can change these scales, so if I change the range on channel 2 to 2 volts per division, each of these divisions is now worth 2 volts. I can use these pointers on the left to move the waveform up and down. That corresponds to changing the offset in the control panel. The vertical scale for the selected channel, in this case the blue line channel 2, is shown on the vertical scale. If I select the other channel, now I'm showing the scale for channel 1. The trigger controls are up here. They set a condition on the waveform that will appear as time t equals 0, indicated here and by this upside down black triangle. Basically, what's happening is that the scope is taking snapshots of the waveform and displaying them in the main window like the frames of a movie. The trigger tells the scope how to line up the frames of the movie. So this is 0 time. That's based on channel 1 being a rising edge where it's increasing at a level of 0 volts. If I change this, say 0.2 volts, that moves the trigger position. Now time t equals 0 is set where channel 1 is 200 millivolts. If I change this to a falling edge trigger, this is now where this waveform is decreasing. I can also change the trigger level with this icon over here. If I move the trigger level beyond a voltage that's actually measured, now the scope doesn't know where to line up the frames of its movie. They'll wander all over the place. I'll restore this to what I had before. Now I need the current through the unknown resistor, which I can get from the measured voltage across the known resistor and its resistance. I can do this by creating a math channel. Click on the Add Channel button. This is a custom mathematical operation. To change the operation, click down here. You'll get a dialog box. The current is channel 1, C1 over 100 ohms. I should actually measure the resistance and use an exact value here, but this is just a demo. This is now a current, so I'm going to change the units to amps and say OK. The range is inappropriate for these small currents. I'll change the range to, say, 5 milliamps per division. Now we have the voltage across the unknown resistor, which is the blue line, the current through the unknown resistor, which is the red line. We can plot the voltage as a function of current using an XY plot. To get that, go to View, click on Add XY. Now we choose the channels that we want on the horizontal and vertical axis. If I want current on the horizontal axis, I change this to M1, which is the math channel we created. The slope of this line is the resistance. These scales are a little bit awkward. I can change the scales in the XY plot by changing the scales in the main window. For example, if I use 2 milliamps per division, I probably get something that's a little easier to read.
Action.
We can use this process to plot the voltage-current relationship for an arbitrary circuit element. This is the appropriate circuit to use. We have a voltage source, V sub s of t, that changes as a function of time in series with a known resistor R and the circuit element we want to characterize. We measure both the voltage across the resistor, V1 of t, and the voltage across the unknown element, V2 of t. The voltage across the resistor is used to determine the current by dividing V1 by R. We then plot that current versus the corresponding voltages V2 to get the voltage current characteristic for the unknown circuit element. Voltage current characteristics of elements or combinations of elements are important in system analysis and design. These curves tell us what voltage we need to apply in order to get a desired current, and vice versa. Those concepts can also be used to experimentally generate a simple model for a complicated circuit.